In this video I'm going to cover the topic of electrophilic addition, one of the reaction mechanisms in the AQA AS specification for chemistry. So with any of these sort of topics where you've got new words like electrophile and maybe addition within the concept of this reaction mechanism, you've got to think, well, what do the terms mean? And actually once you sort of get your head around what the terms mean, it opens up and actually makes the mechanisms that much more sort of logical. So we'll start with the term electrophile. So an electrophile, what's that going to be? Well, if you've already looked at nucleophilic substitution, then you should know what a nucleophile is, and you should know that a nucleophile, the way that it can be defined is as an electron pair donor, but also it's something that is attracted to areas of positivity. And so really electrophile is the complete opposite. It's attracted to negativity. So I'll just put attracted to negative, and I'll put that in speech marks for now. In terms of a definition, it's an electron pair acceptor. So it is the complete opposite of a nucleophile. On the other hand, addition, with any addition reaction, and that could be addition polymerization as well. Any addition reaction, we find that things are added together. Surprise, surprise. But what that means is that when they're added together, we get nothing else produced. So two things are added together, so it's almost be like sort of A and B go to C. There is only one product, and that's really, really important. That's the kind of reasoning for the addition now. So we've got one thing being added to one thing. One of these is going to be our electrophile, creating one product. Now in the case of electrophilic addition, the organic side of it, the organic reactant, is always an alkene. Note alkene, not alkane. And so we're looking for something, for example, ethene. So we're looking for a molecule which contains that classic double bond. And it's this double bond here that actually links through to this attracted to negative. So our electrophile is invariably attracted to this area here, the carbon-carbon double bond, where we have what we can class as an electron dense area, or an area of high electron density, and that's the key thing about our carbon-carbon double bond. As with nucleophilic substitution, again, there are three particular electrophiles that you must know that could be asked in your exam. The first two that we'll look at are more common. The third one, I should say, less common, but it has come up in the past. And these electrophiles are as follows. So we have, first of all, bromine molecule, Br2. Never ever write bromine as a standalone thing. The only time you'll see that bromine on its own would be if it was an ion or if it was a free radical. If we're talking about general bromine, we're going to be looking at bromine as in Br2, the bromine molecule, this diatomic molecule, so looking like that with our little covalent bond in the middle. The other one, an electrophile, hydrogen bromide. Final one, sulfuric acid. Now what I'm going to do is I'm going to work through these in this order, starting with bromine, showing you the mechanism, which actually is exactly the same for all three, but there's a slight different reasoning between this one and these two as to how the mechanism starts. But once you've got the mechanism down, there'll be no issue actually applying it to any sort of scenario, whether that be different molecules from these as well. You've just got to realise that you're dealing with electrophilic addition, and that's where the kind of the alkene. See an alkene in the reaction as a reactant, it's going to be electrophilic addition. So let's have a look at this mechanism then. Okay, so this is our starting position for our mechanism. We've got, in this case, a molecule of ethene, and we've got the bromine molecule there as well. So the Br2, C2H4. Now at this point you might be thinking, or might not, but you hopefully would be thinking, well, how can this occur? How can this as a mechanism actually happen? If you think back to the nucleophilic substitution, or if you've not done it, look at it. In that case, we have a difference in polarity, which leads us to, for the nucleophilic attack to take place. In this case, there's no difference in polarity within my bromine molecule. I've got certainly no permanent dipoles here at all. And what actually we find is that if you imagine these two things sort of floating around the screen, as they come close to one another, these electrons actually cause repulsion within the bromine molecule, and that repulsion means we end up with an induced dipole. Now what I'm saying in this sense, if I'll rub this out and make it a little bit clearer. So what happens is it pushes the electrons from one toward the other. So in this case, what I'm saying is the electrons are being pushed from the top toward the bottom, and this is inducing a dipole. And we now have this region here of delta positiveness, delta positivity, and this region of delta negativity at the bottom here. And this now means that actually a reaction can take place. And this is the starting point now. You don't need to include these in the mechanism, but I always think it's a good idea to do so, because it just gets it a bit more clear in your head. So first step, do it in a different colour. First step, always from the double bond, a nice curly arrow toward the bromine here. So what we're going to find is we're forming a bond here, and in doing so, these electrons are ejected and they move on to this guy here, onto this bromine. So what we end up with is an intermediate stage which you must include, and it looks something like this. Single bond now, we've got rid of that double bond. This pair of electrons here, let's go for a different colour, this pair of electrons has moved and has allowed for a bond to be formed between the carbon and the bromine. So we now have a bromine attached, as well as obviously our two hydrogens from before, 1 and 2 there, and over here we have a carbon with our two hydrogens. Now we're missing any sort of bond here at all. What that means is that at this point we've created what's called a carbocation. So this here is now it's actually a positive carbon. The reason for that is that if you can imagine within this carbon-carbon double bond here, within this single covalent bond of the two, one of those electrons from the pair was from this carbon, for example. And what we've done is we've taken both of those electrons and we've switched them round. So the electrons were here, we've now moved them, and they're now here. Well, this carbon is still it still has that same electron from before involved in the bond. But this carbon now has lost that electron over to here, and it's, if you like, been donated to bromine to allow for the bond to be created, which means this carbon is deficient. Now, if you didn't understand that, firstly I apologise, but secondly you don't need to. You just need to be able to include this plus here. That's very important because that carries a mark on its own. You must have that, and it must be on the right carbon, which in this simple example here could be on either, but you just switch it completely around. It would be the same molecule. What we find then is we now have a bromine, negative ion now, and it has a cheeky little lone pair. And what can happen now is that this comes round, and now we are doing the opposite. The bromine is now in essence acting as a nucleophile. It's donating that lone pair to here to create a bond between there. So, and you don't need to draw the product, but I will in this case. So we go in between there, and then here we end up with carbon, carbon, hydrogen up here, another hydrogen up here, hydrogen, another hydrogen, and then finally two bromines now. So from what I said at the start, you can now see where that addition is coming in. We started with two molecules, we now end with one molecule. There is no waste product, there is nothing else produced, just this. And in this case we have dibromoethane. So dibromoethane, and I should of course include the numbering here. 1, 2, dibromoethane. Oh, missed the O there. The other time you've actually seen this, and this is a reaction that people invariably they don't remember this, you've seen this back in sort of year 10 time, and this actually here is the reaction, or the test I should say, which is ultimately a reaction, but the test for an alkene. So if you remember, bromine water goes from orange to colourless, that standard thing, test for an alkene. Well, this is it. This is actually why it's happening. The bromine is being added onto the double bond, across the double bond, forming a new molecule, thereby changing, obviously, the alkene into the dibromo alkane. And the bromine, in doing so, the colour changes from orange to colourless. So this is that test that you've seen time and time again. Be aware at this point that although I've used bromine here, there could be any molecule. It could be chlorine, it could be any of the, well, that's about it really. Just chlorine would be the other one I can think of. Possibly fluorine, I guess, if they wanted to do that, but you're more likely to see bromine or chlorine in these examples. And again, all you do there, you just change the bromines here for chlorines. Everything else would remain the same. Negative there, arrows in the same place, lone pair of electrons and all the rest. So what you could get, you'll find for this question here, you potentially could get 4 marks for this. 1 mark for your initial arrow, 1 mark for the second, 1 mark for this what's a structure mark, and then finally a mark there as well. So 4 relatively straightforward marks. Okay, what I'll do now is we'll look at the hydrogen bromide example, and then we'll finish off with the sulfuric acid molecule. Okay, so stick with ethene again. This time we have hydrogen bromide reacting with ethene, and what we find is that this is actually a little bit more straightforward to understand, because here we have a difference in electronegativity between my hydrogen and my bromine. Therefore we have a more naturally occurring, if you like, polarity there, a permanent dipole between the hydrogen and the bromine. And so exactly the same though as before, with the obviously the delta positive and delta negative, we have the exact same reaction. Find my red. That comes down to here, that goes across to there. We form the intermediate, and the intermediate this time is again, well, slightly differently than before, but similar concept. And it doesn't matter whether you do this on the other side or not, I just tend to prefer doing this. Positive there, carbocation, as before, get my bromine involved, negative ion, lone pair of electrons, arrow across, and there we go. 1 mark, 2 mark, structure mark, 4th mark for the arrow. 4 fairly straightforward marks. The mechanism hasn't changed at all. We have used exactly the same mechanism. There is absolutely no different besides the starting molecule here. But the arrows are exactly the same. You could actually have it as a template and just put your various atoms or ions in the right place, and you would be away. There is one extra point that can be drawn into the hydrogen bromide, and that is that whereas with the bromine we've got 2 of the same atom being added across, and so there's no difference. And in this case, with the simple ethene starting product, it doesn't matter where the hydrogen and the bromine goes, we're going to get the exact same thing occurring. If we started increasing the size of the molecule, and say we took propene for an example, then actually we find that it changes slightly. And what we would get is that, let's take propene. So we've got our molecule drawn, exactly the same concept as before. My hydrogen bromide comes in, and it's going to follow exactly the same pattern as before. Now, what we can find is that if we think about this now, the hydrogen has 2 potential options of where it can bond, and that will create 2 different molecules. We could have, and I'll draw the 2 options out here, the 2 intermediates. So we could have that, or we could have that. Now, it's quite difficult to see just in this case. What I'm got here is that this is the hydrogen that came from the hydrogen bromide in this case, and this is him in that case. So you can see he can either join to this carbon in this first example, or he can join to this one, and in doing so we form a different carbocation, and that's a very, very important difference. And if the bromine were to join here, we would form 1 bromopropane. If it were to join here, we would form 2 bromopropane, 2 different molecules entirely. And so we've got a positional isomerism occurring there. Now, in reality, it's not quite as straightforward as it could just join in either place. The carbocation that is produced as the intermediate will be the one that is more stable. And the way that the stability works is more stable equals more alkyl groups attached. I should say more stable carbocation equals more alkyl groups attached to that carbocation. So if we would look at this example here, choose a slightly different colour, this carbon here has one alkyl group. This whole thing here, the whole thing around, that is an alkyl group. Yes, it's an ethyl group, it doesn't matter, it's an alkyl group, it's just treated as one alkyl group. And what we could say is we would say that this, because it has one alkyl group attached, this is a primary, terrible P there, this is a primary carbocation. On the other hand, this carbon here has 1, 2 alkyl groups, both methyl groups, and you might be thinking, well, this is an ethyl, that's bigger, that's better. No, it's the number of alkyl groups that makes the difference. So 2 methyl groups here means that we have a secondary carbocation, and there's a shorthand way of writing these. Primary you can write as 1 degree, and secondary you can write as 2 degrees, and it links exactly into the 1 is the number of alkyl groups, the 2 is the number of alkyl groups. And so what we find is this is the preferential carbocation that will be produced because it is more stable. And the reason it's more stable is because these guys here, and I'll choose another colour, these alkyl groups, we get something called the inductive effect occurring. And to put it more simply, this is more advanced really than you need to know, but these push electrons, if you like, onto the carbocation, therefore spreading electrons around the molecule more evenly, and that creates a more stable overall molecule. So this is the one to choose, and therefore we'll ultimately end up with, let's see if I can find another colour, yep, I will ultimately end up with, not the clearest one in the world, but the bromine attacking onto this one. And so my major product, if you like, my major product is 2-bromopropane, and my minor product would be this one up here, the one that's less likely to be formed, minor product 1-bromopropane. So that's the hydrogen bromide. So you can see it's a little bit more advanced, but actually it doesn't. There's not a huge amount extra. It's just this part here with the stability. And once you get your head around the idea of the primary versus secondary, and we could go one further and say, oh, we've got tertiary, which would be 3 degree, then that would be 3 alkyl groups joining. That's the most we can get to on this point with the carbocation. So tertiary. If you ever see quaternary, that just means 4, as opposed to the tertiary being 3, secondary being 2, primary being 1. So that's really the key thing here, and that doesn't come up very often on exams, to be perfectly honest with you. In a more simple way, you would just have to be able to add the hydrogen bromide onto the molecule. Be aware they may give you a product which they want you to form, so they might give you a starting point. They may give you that you're producing 2-bromopropane, and so you need to draw your mechanism as is appropriate. You can't draw it the wrong way around and somehow miraculously form the product they want you to. The mechanism must actually create the product that they're asking for, and that's how they can get around needing to ask you or needing to delve into the idea of stability if they were to wish. Okay, so finally, gone with that one long enough, we've got sulfuric acid. Okay, so we've got an ethene molecule as before, and this time we're going to have a sulfuric acid molecule. Now, what I would advise in an exam, and I would advise this, but if you really can't remember how to draw it, then don't. I would advise that certainly you learn the structure of the sulfuric acid molecule. And it looks like this. So we've got H2SO4, H2SO4. You could draw it as this, but it's a little bit sort of sloppy. I'm not entirely sort of happy with that, I would stick with this molecule here, in all honesty. Also because it allows you just to see a little bit more clearer kind of what you've got, and similarly to the hydrogen bromide, we've got a region where we've got polarity here. Electronegative, not very electronegative. Therefore, we've got a delta negative region, we've got a delta positive region. And exactly as with the previous two, we get that bond coming in there, curly arrow. We get that moving onto there. We have an intermediate, exactly as before. And I'll stick with what I've done previously. Carbon, hydrogen, carbon, hydrogen, carbon, hydrogen, carbon, hydrogen. Oh, hydrogen there. Positive region there. This time we have obviously a negative oxygen there, going to our sulfur, oxygen, hydrogen, like that, and finally we would get, this is a lone pair by the way, terribly drawn, but that's a lone pair. We would get that moving across there. What we produce here, and I'm going to draw this out for you, sort of anyway. So what we get is we have our carbon, hydrogen, 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 carbon, hydrogen, hydrogen. I've lost my hydrogen up there. And then onto here we have this O, and we would have SO2OH. I'm actually going to change this thing here. If you want to draw it as a shorthand, don't draw it like that. In fact, I apologise for this. Do it as HO SO2 OH H2SO4. Draw it like that. I would stick to keeping the whole molecule drawn out, unless you know you're going to make mistakes. But to be honest, there's learning that. There's not a huge amount to learn here. Just get by and just do it really. And this is what you would produce here. So, and this is named as per like an alkyl group here. So it would be called ethyl hydrogen sulfate. A couple of things really about this. So we've got our ethyl hydrogen sulfate. What we can do, and this actually comes up sort of in, it's kind of in the alcohols topic as well, in the idea of hydrating an alkene into an alcohol. If we were to add water now, so if we add H2O, we would produce, in this case, CH3, CH2OH. We produce ethanol, and actually we reform. This would reform the sulfuric acid, and if you've done the alcohols topic already, then great. If you haven't, you will come on to this. But in the production of ethanol from ethene, we use concentrated sulfuric acid or phosphoric acid. But in this case, we could use the sulfuric acid as a catalyst, and you can see this is actually the mechanism for how it would work. There would be a further mechanism occurring here, which you would not need to know. In terms of an exam situation, if they're asking you to use the sulfuric acid as the electrophile, they're expecting you to end here, not to draw a mechanism to take it to the alcohol. They're expecting you to understand that this can go to an alcohol, but not to draw the mechanism for that. The mechanism stops here, doesn't go any further. Okay, quite a lot there, but hopefully that's been of some help. And there you have it. That's electrophilic addition.